Let's start. Number 1. Brown dwarfs approximately equals 0.01 to 0.08 sun masses. These are almost stars. They form like stars from collapsing gas, but most never get hot enough in the core to sustain normal hydrogen fusion. Some burn deuterium early on, and the heaviest can briefly burn lithium. Then they cool for billions of years, getting redder and fainter. In surveys, they show up best in infrared, and astronomers even group many of them into cool spectral families, often called L, T, and Y dwarfs, as they chill over time. Some have patchy clouds and weather-like variability, making their brightness flicker as they rotate. Number 2. Red dwarfs approximately equals 0.08 to 0.5 sun masses. The most common stars in the Milky Way. Red dwarfs are small, cool, and absurdly fuel efficient. Below roughly approximately 0.35 sun masses, many are fully convective, meaning their interiors mix more thoroughly, helping them use hydrogen steadily for an incredibly long time. Lifetimes can be tens to hundreds of billions of years, and the tiniest may last far longer than the universe's current age. Because they're dim, their habitable zones sit very close in, where planets can be tidally locked and where stellar flares matter more. Many red dwarfs are magnetically active, blasting nearby planets with UV and particles. Great for drama, less great for fragile atmospheres. Number 3. Orange dwarfs approximately equals 0.5 to 0.8 sun masses. Underrated middle children, brighter and often calmer than many red dwarfs, but longer-lived than sun-like stars. Orange dwarfs can keep stable output for very long stretches of time, so they're popular in best star for habitability discussions. They still end gently, expand into a red giant later on, shed outer layers, and leave a white dwarf behind. Number 4. Sun-like stars approximately equals 0.8 to 1.2 sun masses. This is the classic stable main sequence life, roughly 5 to 15 billion years fusing hydrogen in the core depending on mass. When core hydrogen runs low, the star swells into a red giant, ignites helium, and later sheds its outer layers. The exposed core becomes a white dwarf, about Earth-sized but with roughly half a sun's mass packed inside. The expelled gas can glow as a planetary nebula, which is basically the star's goodbye photo. Number 5. Intermediate mass stars approximately equals 1.2 to 8 sun masses. Add mass and everything speeds up. These stars are much brighter than the sun, but their lifetimes drop to hundreds of millions, or a couple billion years. Many are A- and early F-type stars, hotter, whiter, and more luminous. Late in life, they can balloon into giant or supergiant phases and lose a lot of material through winds and pulsations. Some also become famous standard Kendall variables during their evolution, where pulsation periods link directly to luminosity. Most still end as white dwarfs, just more massive ones, because their cores usually don't get heavy enough to collapse into neutron stars. The boundary isn't razor sharp. The highest mass members can develop unusual cores and sit near rare in-between outcomes, depending on composition and mass loss. Number 6. Massive stars approximately equals 8 to 20 sun masses. Cross this threshold, and the ending changes completely. Massive stars run through fusion stages like a speedrun, hydrogen to helium, then heavier fuels in shells, building an onion-like structure. You'll often see them as blue supergiants or red supergiants depending on their stage and internal mixing. Eventually, an iron core forms, and iron fusion can't support the star. The core collapses in seconds, launching a shock and a flood of neutrinos, triggering a core collapse supernova that seeds space with heavy elements and leaves behind a neutron star or a black hole, depending on the final core mass. Number 7. Very massive stars approximately equals 20 to 60 sun masses. These stars are brutally bright and brutally short-lived, often just a few million years. Their radiation and winds can strip off outer layers, sometimes revealing a Wolf-Rayet star, a hot, exposed core blasting material into space at high speed. Stripping matters because it changes what the explosion looks like and what's left behind. If rotation and geometry cooperate, some of these systems can produce the most extreme high-energy events we observe. Their deaths can be energetic supernovae, but some may fail more quietly, collapsing into a black hole with much less visible fireworks. Number 8. Hypergiants and the upper limit approximately equals 60 plus sun masses, with births up to approximately 150 to 200. Hypergiants are the unstable giants of the zoo. They can be hundreds of thousands to millions of times brighter than the sun, with enormous bloated envelopes that pulse and shed mass in eruptions. Some are surrounded by giant shells of gas and dust they've thrown off, like a permanent smoke cloud you can't turn off. At these extremes, stars live close to a physical limit where radiation pressure can compete with gravity in their outer layers, which helps explain why nature doesn't easily build stars of any mass. Metallicity matters too. In metal-rich environments, winds are stronger, so stars slim down quickly. Their final act depends on what the core becomes after all that mass loss. Many end as black holes, and the most extreme low-metal cases may hit rare instabilities that can produce unusually powerful explosions. Subscribe for more quick visual space explanations and drop a like if this helped. It really supports the channel.